Welcome back, everybody, to the second episode, which we're gonna call "What's Up with the Sound Waves." So, maybe you think you don't know why we're doing this because you already did the sound waves in the lecture, but I can imagine that some of you, at this point, when we did this in the lecture, were still a bit lost about the procedure that was going on, and in the end, the dispersion relation of the sound waves it kind of popped out simply like from a virgin birth or something. So we try to do now the same procedure that we did in the lecture, just with a constant background flow that does not change anything in the end, as you will see. But this time we will be aware of what we're doing, and yeah, just we're gonna realize that we actually learned something in the last 2 weeks about this stability analysis. If you feel that you already understood everything the first time that you saw the sound waves, then of course feel free to skip this video. It's not gonna be entertaining or something. So to study these sound waves, we will make the simplification of just regarding one dimension. That's completely enough, and we will follow the procedures that I described in the first video. So we're gonna start asking the questions: which are the relevant equations that we have to linearize? And since we will regard an isothermal case, which means that the temperature does not evolve and hence the internal energy does not evolve, we are limited to two equations, which is the continuity equation that is written down here, and the second equation is the momentum equation that you can see here. We don't have a field of gravity, we don't have viscosity, we don't have anything on the right hand side, but the gradient of the pressure, which is important since we're getting sound waves. Okay, the second thing that we need to do is to perturb the relevant quantities. Which are the relevant quantities here? It is the density, which we will split into a background and to the perturbation. It is the velocity, which we will also split into the same things. And then we have the pressure. We use the formula for the isothermal pressure, where the pressure is simply the sound speed squared times the density. And the density itself, as we saw before, is a background plus a perturbation. So, as always, we make the assumption that the perturbations are much smaller than the background fields. And I was wondering in how far this is true in the case of sound waves, for example, on Earth. And I looked up a few examples, and for example, the stun grenade, if we think of it, how much does it perturb the pressure when it makes its sound? We will find out that the perturbation of the pressure in comparison to the atmospheric pressure that we have is only 5% for a stun grenade, which is pretty loud. The loudest human voice, for example, it is only 0.1% of the atmospheric pressure, and the threshold when we start to hear something at a really sensible frequency, it is only 10 to the minus 10 of the atmospheric pressure. So our ear is really well designed to detect like the smallest perturbation of pressure. If you're interested in that stuff, you can go to Wikipedia. There's like this sound pressure, and there are some examples, for example, a trumpet or a rifle or something. Okay, so the next thing is that we're gonna make some assumptions about the quantities that we're looking at. We're gonna say that the background quantities, they are constant in time and in space. So this means that the relative of rho and v, and also the pressure, of course, of the background fields, both in time and in x, are going to be zero. This has a consequence that these two equations here that you see in the top left corner, they are satisfied for the background field automatically, since every single term turns zero. Okay, and with this now, one more thing. In contrast to the thing what you did in the lecture, we will say that the x derivative of the velocity is zero, but the velocity itself we don't set it to 0. We say there is some real velocity as the background flow, which we're gonna keep throughout the process. Okay, so next step is to linearize the equations. And we will do this by inserting the perturbations, the expressions of the perturbed quantities into equation 1 and 2. So let's start with equation 1. Here we see what happens if we insert these expressions, and then we reformulate this, and now we can go and take a look at the quantities that we can cross out, which are the time derivatives of the background fields, what you can see here, and also the quadratic terms of the perturbations, because this is the linearization. And then we're left with these parts. So now we have another x derivative of a background field here, and we have another x derivative of the velocity here, and we are left over with this equation for the coming from the continuity. Okay, then the second equation looks like this, and again we do the same thing, time derivative of the velocity background, x derivative of the velocity background, and here again x derivative of the density. Then we're left with this, and now it is important to take a short look what happens if you have a perturbation multiplied by the gradient or by the time derivative of a perturbation, because even though the perturbation might be really small, that does not automatically mean that also its derivative is really small. There are functions that have a really small absolute value, but the derivative can be quite large. However, if we take a look at the expression that we know we're going to insert afterwards, we see that if we take the derivative either in x or in t of this expression, it's going to go to the order of the amplitude of the perturbation squared. So this term is also of the order of the perturbation squared, and therefore we can neglect it. This is what then happens here, and also here, and also here. Okay, so then we're left with our second equation, which looks like this. Alright, now we arrived at our two linearized equations. This is now the point where we can think about the expressions for the perturbations that I showed already before. So the perturbations, they are just these in this waveform. If you are wondering why we use these expressions, go back to the first video, I explain it there. And then we see that if we put a gradient, or the x derivative in this case, onto these perturbations, it will just turn into ik. And if we put a time derivative on it, it will turn into I omega. Now, you will see sometimes these perturbations are defined in different ways. Sometimes it is kx minus omega t. Sometimes the I only is multiplied onto the kx, and the omega t is not imaginary but real. So it always depends on how you define your perturbations, and you have to change these expressions for the derivatives adequately. But now we define it like this, and we can see that we can replace the derivatives in equation 1 and 2 by ik and by I omega. So let's do this. Equation 1 turns into this, and equation 2 turns into this expression. Then we restructure the equations in a way that we isolate the omega terms on the left hand side, and on the right hand side we write all the other terms. So the first equation then looks like this, and the second one like this. Now, if we look closely, we realize that all the terms have this I in it, so we can just divide both sides in both the equations by minus I to simplify the things in a way, and I'm left with these two equations. Now, a set of equations, no matter if it is 2 equations or 10 equations, it can be written in a matrix form. So that's what we're going to do. The right hand side of the equation, we write it as a matrix multiplied on the perturbation vector. So the first entrant in the perturbation vector is delta rho, and the second entry is delta v. And this means that the first argument in the matrix has to be k times v0 because it is multiplied onto delta rho. If we continue with that, we will find that the matrix equation in the end looks like this. So on the left hand side, we simply have minus I omega multiplied onto the perturbation vector, and on the right hand side, we have this matrix. Now, the procedure is quite simple from here, because the only thing that we have to do is to solve this eigenvalue problem, which is a well-defined problem you can find in linear algebra or in some textbooks. For this we have a matrix and we have an eigenvalue. And we know that the eigenvalue, to get the eigenvalue from the matrix, one has to solve the determinant of the matrix minus the eigenvalue times the unity matrix. And if we put into this determinant here the value minus omega for lambda, we can calculate the determinant and we get a characteristic polynomial which looks like this here. And this is simply a quadratic equation we can solve by using, for example, the PQ formula, and we get a relationship between omega and k that looks like this. And in the end, a dispersion relation for the sound waves in a background flow that has the velocity v0. So what we realize is that now the dispersion relation, it has two solutions. One describing a sound wave that is traveling with the flow, and one that is describing a sound wave that is flowing against the flow. So while initially without the background flow the sound waves that travel left and right, they have the same structure, the background flow changes this property, and this describes something like a Doppler effect inside the fluid. So here we have taken a look at probably the most basic example of perturbation analysis. But by doing this, we found all the most relevant steps and basically the fundamental procedure of this analysis. And now, whatever we do, like whatever system we analyze, this is going to be the fundament, and we just have to adapt the equations, maybe use the background conditions, maybe use some boundary conditions, and from that, doing the same, we will find a dispersion relation that tells us something about the physical behavior of this system. Now the sound waves, they are already quite interesting and important for physics, but it becomes a bit more challenging when we take a look at, for example, two fluids. So the interface of two fluids, how will it behave if the fluids have a shear, which means like they have a different velocity, or if fluids have a different density, and maybe the more dense fluid is located on top of the lighter fluid. This will lead to things like the Kelvin-Helmholtz instability or the Rayleigh-Taylor instability, and I hope to find a time to post another video explaining more about this, because these are examples that show some instability behavior that is also quite interesting for astrophysical problems.